Today we're diving into a paper that explores a novel approach to improving the quality of instruction tuning data for large language models. The paper, Selective Reflection-Tuning, Student-Selected Data Recycling for LLM Instruction Tuning, proposes a collaborative method between a teacher and student model to refine existing data. What's the main challenge that this paper addresses?
The paper tackles the issue of data quality and instruction tuning. While many methods focus on improving data quality, they often overlook the compatibility of the data with the specific student model being fine-tuned. This can lead to inefficiencies and suboptimal performance.
So how does this paper propose to address this compatibility issue?
The paper introduces a teacher-student collaboration pipeline. The teacher model, typically a well-trained LLM, reflects on the instruction and response of a data sample and generates improved versions. The student model then evaluates these improvements based on its own statistical attributes, deciding whether to incorporate them.
That's interesting. Can you elaborate on how the teacher model reflects on the data?
The teacher model uses specific criteria to analyze the instruction and response. For example, it might assess the complexity of the instruction, the level of detail required, or the ambiguity of the instruction. Based on this analysis, the teacher model generates a new instruction and response that it believes are better suited for the task.
And how does the student model evaluate these improvements?
The student model uses two metrics: instruction following difficulty, IFD, and reversed IFD, RIFD. IFD measures how difficult it is for the student model to generate the response given the instruction. A higher IFD score indicates a more challenging instruction.
So the student model prefers data with higher IFD scores?
Not necessarily. The student model also considers RIFD, which measures how much the response contributes to predicting the corresponding instruction. A lower RIFD score suggests that the student model can easily deduce the instruction from the response, indicating that the sample is feasible for the student to learn.
It seems like the student model is looking for a balance between challenging instructions and feasible responses.
Exactly. The student model aims to select data that is both challenging enough to promote learning and feasible enough to be effectively processed.
This selective data recycling process sounds like it could be quite computationally expensive. How does the paper address this?
The paper emphasizes that the method is designed to be sample efficient. The student model only needs to evaluate a small number of data samples, as the teacher model has already pre-filtered the data.
So the teacher model acts as a kind of pre-processor, reducing the workload for the student model.
Yes, that's a good way to put it. The teacher model helps to identify the most promising data samples, allowing the student model to focus its efforts on those that are most likely to be beneficial.
Can you provide some examples of how this method is applied in practice?
The paper demonstrates the effectiveness of the method by applying it to the Alpaca and Wizard LM datasets. The results show that the student models trained on the selectively recycled data outperform other models, even those trained on larger datasets.
That's impressive. What are the key contributions of this paper?
The paper introduces a novel teacher-student collaboration pipeline for improving instruction tuning data. It also proposes the use of RIFD as a metric for evaluating the feasibility of data samples. Finally, the paper demonstrates the effectiveness of the method through empirical results.
Are there any limitations to this approach?
One limitation is that the data samples selected by different student models will vary. This means that the IFD and RIFD scores need to be recalculated for each new student model. However, the paper argues that this is still more efficient than other data generation methods.
So the method is not entirely model agnostic, but it offers a significant improvement in efficiency.
Yes, that's correct. The paper presents a promising approach to improving the quality and compatibility of instruction tuning data, which could have a significant impact on the development of more effective and efficient LLMs.
This is a fascinating discussion on the technical aspects of this paper. Thank you for your insights.